Hello friends, let's continue with another problem on sampling theorem. In this problem, we shall show that even though as per bandpass sampling theorem, it is possible to perfectly reconstruct a bandpass signal from its samples by sampling it at a rate lower than the Nyquist rate, not all frequencies below Nyquist rate can be used. Before we go for the problem, let us first recollect the statements of low-pass and bandpass sampling theorem. As per low-pass sampling theorem, a band-limited signal, which may be a low-pass signal or a bandpass signal, which is band-limited to W Hz, can be perfectly recovered from its samples by low-pass filtering if the samples are taken at a rate greater than or equal to twice the maximum frequency of the signal. As per bandpass sampling theorem, on the other hand, a bandpass signal of bandwidth B Hz and maximum frequency W Hz can be recovered from its samples by bandpass filtering if the sampling rate is equal to twice the maximum frequency upon some integer k, where k is the largest integer not exceeding the ratio W by B. All higher sampling rates are not necessarily usable unless they exceed twice the maximum frequency as per the low pass sampling theorem. Let us show this clearly through a problem. The problem is as follows. Consider a bandpass signal m of t with the spectrum m of f shown in the figure here. Check the bandpass sampling theorem by sketching the spectrum of the ideally sampled signal m delta t when the sampling frequencies are taken as 25 kHz, 45 kHz and 50 kHz. Also indicate if and how the signal can be recovered. So clearly the signal shown is a bandpass signal with maximum frequency W equal to 25 kHz. The bandwidth of the signal, which is B, equal to the maximum frequency 25 minus minimum 15 equal to 10 kHz. This is the bandwidth, 10 kHz. Now, as per the bandpass sampling theorem, the sampling frequency Fs is given by 2 times W by K, where K, let us compute K separately here, K is the floor of W by B. That is, W is 25 kHz and the bandwidth is 10 kHz. So the floor of 25 by 10, which is floor of 2.5, that is equal to 2. The largest integer not exceeding 2.5 is 2. So the sampling frequency as per bandpass sampling theorem is 2 times W, that is 25 kHz, upon K, which is 2, and that is equal to 25 kHz or 25 kilosamples per second. We shall show that when we sample this signal at 25 kilosamples per second through bandpass filtering, we can recover the signal. So look at the first figure here. We know that the process of sampling results in multiple copies of the original spectrum. The spectrum shown in solid lines here is the original spectrum. So you can see it, this and this. This is the original spectrum, m of f. And because of sampling, this spectrum gets repeated at all integer multiples of sampling frequency, which in this case we have taken to be 25 kHz. So we get this spectrum with respect to 0 here, from 15 to 25 kilohertz on the positive side and from minus 15 to minus 25 on the negative frequency axis. Now when 25 kilohertz is the sampling frequency, the same spectrum is repeated around 25 also. So just as we had this part with respect to 0, it was from 15 to 25. So with respect to 25, it will be from 25 plus 15 to 25 plus 25, which is 25 plus 15 is 40 and 25 plus 25 is 50. So we get this copy, this version. Similarly, if we look at this part with respect to 0, it is from minus 15 to minus 25. So with respect to 25, it will be from 25 minus 15 to 25 minus 25. So 25 minus 15 is 10 and 25 minus 25 is 0. So we get this copy, this one. Now if we look at the negative part with respect to minus 25 kilohertz, we get the copy of the spectrum from minus 25 plus 15 to minus 25 plus 25, which is from minus 10 to 0. Similarly, from minus 25 minus 15, which is this minus 40, to minus 25 minus 25, which is minus 50. So we get this copy. When we take 50 as the reference, because it is 2 times fs, so with respect to this, the same thing happens. 50 plus 15, that is 65, to 50 plus 25, 75 will get a copy. Similarly, 50 minus 15 to 50 minus 25, so we get a copy from 35 to 25. Similarly, with respect to minus 50, we get from minus 35 to minus 25 and so on. So this is the spectrum of the sampled signal when the sampling is done at a rate 25 kilohertz. Clearly, if we use a bandpass filter as shown here with lower cutoff frequency between 10 and 15 kilohertz and the upper cutoff frequency exactly equal to 25 kilohertz, we are able to extract the original spectrum and therefore the original signal. However, if we take the sampling rate to be 45 kilohertz as shown here and follow the same procedure to get the spectrum of the sampled signal, we see that there is an overlap between 2 successive copies of the spectrum and therefore we cannot extract this spectrum correctly by using any filter and there will be distortion. However, if the sampling rate is taken to be exactly equal to the Nyquist rate, which is 2 times W, because the maximum frequency W is 25 kilohertz, so 2 times W is 50 kilohertz. So if we sample it at 50 kilohertz, we get this spectrum. Clearly, there is no overlap of successive copies and we can extract the signal, the spectrum back by low pass filtering with the cutoff frequency of the low pass filter taken as 25 kilohertz in this case. If the sampling rate is greater, then there will be some gap between two. The low pass filter that can be used need not be an ideal low pass filter and we can still recover the original signal. The point is that for a bandpass signal, it is possible to sample at a rate less than the Nyquist rate. Still we can recover the signal through suitable bandpass filtering. However, not all other frequencies higher than this frequency in this example are useful unless they exceed or equal the Nyquist rate. Another important point to note here is that when we are sampling at a rate 25 kilohertz, which is less than the Nyquist rate, here we have to use a bandpass filter. You can see clearly if we use a low pass filter, then we will also be getting back some undesired frequencies which were not present in the original signal and therefore there will be a distortion. So I hope this point will be clear and the difference between the low pass sampling theorem and bandpass sampling theorem is clear. It can be noted that bandpass sampling theorem works with some specific frequencies only below the Nyquist rate, but if we follow the low pass sampling theorem, that is we are talking about sampling rate above the Nyquist rate, it will always work whether the signal is a low pass signal or a bandpass signal. So that's all for this problem and for this lecture. I hope the point is clear. Thank you very much.